Hello everyone, my name is Suki Lee, a PhD student at the University of North Carolina at Chapel Hill. Today, I'm going to present our MobiSys 2020 paper. The title of our paper is Fast and Scalable In-Memory Deep Multitask Learning via Neural Weight Virtualization. Nowadays, intelligent embedded systems can be found almost everywhere around us in the form of standalone devices such as consumer electronics, calculators, routers, aircraft, in-car systems, and thermostats. As deep learning algorithms for resource-constrained systems continue to become more efficient and more accurate, we see an increasing number of intelligent embedded systems such as home IoT devices, social robots, and a plethora of portable, wearable, and mobile devices that are feature-packed with a wide variety of machine learning tasks running on the same device. For example, home hubs like Amazon Echo Show and Google Nest Hub nowadays are performing voice recognition, face recognition, emotion recognition, and gesture recognition in order to closely imitate human assistants. Similar classifiers are running on social, domestic, and personal robots, which also execute robotic application-specific learning tasks such as object detection, place classification, person identification, and scene understanding. However, enabling embedded deep multitask learning is non-trivial due to the limited resources of embedded systems. One of the challenges of embedded deep multitask learning is the small size of memory. Unlike regular computing devices of sufficient memory, such as desktops or laptops, embedded systems with limited memory can hardly execute multiple DNNs in the memory for multitask learning due to their small memory size. Here, for example, 5 scaled-down versions of DNNs whose total memory requirement is 523 kilobyte cannot fit into the main memory of the system, whose size is 129 kilobyte. Similarly, the larger size of 6 DNNs whose total memory requirement is 604 megabyte cannot fit into the main memory of 146 megabyte. As the number of DNNs increases, their scalable packing into the main memory becomes more difficult since the maximum number of deep neural networks that can reside in the main memory becomes more limited. One naive solution to bring multiple DNNs into an embedded system whose size is smaller than the multiple DNNs is to use secondary storage such as flash disk or solid-state disk. However, such a solution, where some of the DNN models must reside in the flash or the hard disk, context switching overhead is extremely high, as the main memory operations are typically 10 times, 100 times faster than accessing flash or hard disk. Hence, the overhead of frequent swapping in and out of DNNs to and from the main memory causes a severe latency, which in turn degrades the responsiveness and usability of the system. There are some existing works that try to solve this problem. The first one is the DNN model compression, which compresses individual DNN models into small sizes so that their total memory size can be reduced. Although this is the most popular approach to employ deep neural networks on embedded systems, it is not scalable since only a limited number of DNNs can fit into the main memory even after compression. Also, it does not perform multitask learning that brings collective performance improvement of DNNs as they are independently trained, which does not increase the accuracy of each DNN by exploiting the commonalities and differences across different tasks. Lastly, the DNN compression requires the modification of the well-established original network architecture, which might cause unexpected behavior at runtime. Also, the compression process requires time-consuming human effort with high cost. Another approach is multitask learning. Given multiple DNNs, it generates a single DNN by jointly training all the DNNs together at the same time. Although the multitask learning approaches can achieve some memory saving by generating a single DNN model for all the tasks instead of generating an individual DNN for each task, it only works for DNNs having similar network architectures performing similar tasks. And multitask learning approaches are not capable of coalescing many DNNs, as DNNs must share a macro or larger structure, for example, first few layers, and thus miss the opportunity to coalesce DNNs when there are similarities between DNNs at a micro level structure. For example, a set of consecutive weights in the way the proposed neural weight virtualization does. Let me summarize the comparison between existing works and our proposal. First, DNN compression can reduce the size of models, but it cannot achieve the benefit of multitask learning because each individual DNNs are trained and compressed in isolation. Next, multitask learning can jointly train multiple tasks and generate a single unified DNN, but only DNNs of similar architectures can be learned together. DNN weight sharing is another approach that reduces the total size of multiple tasks, similar to our proposal. However, it does not achieve execution speedup and it can be only applied to DNNs with similar network architectures. Lastly, although DNN packing approaches can pack multiple DNNs into a single network, the scope and method of DNN packing are limited by network architecture and task type. On the other hand, our proposal achieves in-memory operation, multitask learning, memory saving, architecture agnostic virtualization, and execution speedup at the same time. Let me first describe the problem that our proposal tries to solve. Given the main memory RAM of size X of a system, we want to enable scalable packing and in-memory multitask learning of multiple heterogeneous deep neural networks, DNNs, whose total memory requirement Y is larger than X into the main memory. Here, we have an embedded system with 10 MB of RAM. And we have 4 DNNs whose total size is 40 MB. The goal of in-memory multitask learning is to pack 4 DNNs whose total size is 40 MB to the main memory of the system whose memory size is 10 MB without using secondary storage such as flash or hard disk and perform in-memory multitask learning. To solve this problem, we propose in-memory multitask learning based on the concept of neural weight virtualization. This is how it works. Given a fixed size of memory, we first divide it into several memory blocks, which we call virtual weight pages. For the first DNN, we extract each weight parameter set from the network and group them with the same size as the virtual weight pages in the memory, which we call weight pages of DNN1. And then, weight pages of DNN1 are matched to the virtual weight pages in the main memory. For the second DNN, each weight pages are also grouped and then matched to the virtual weight pages in the main memory in the same way the first DNN did. The overlapped virtual weight pages in the memory between DNN1 and DNN2 are optimized to mu fixed values in such a way that they work for both the DNN1 and 2. In this way, DNN1 and 2 become able to share the same virtual weight pages without experiencing performance degradation. Please note that the summation of weight parameters of two DNNs, which is 36 pages in total in this example, is larger than the total physical memory size, which is 20 pages. We name this process as neural weight virtualization since it virtualizes the same memory page to be shared between different DNNs by allowing the overlapped use of them. Neural weight virtualization is based on the observation that the disparity in weight parameters significance is globally sparse and locally dense. These graphs show the feature information of the weight parameters of the three popular DNN architectures: Inception, ResNet, and VisNet. The feature information measures the importance of an individual weight parameter to the final performance of DNN, which is inference accuracy. Here, x-axis is weight parameters and the y-axis is feature information, where the higher feature information implies that the corresponding weight is more important. As shown in the figure, a few groups of neighboring weights, which are marked with red boxes, dominate in terms of their significance. For instance, the top 5% weights contribute to 90% of feature information in inception, which means that 95% of its memory space can be used by other DNNs if need be, while retaining 90% accuracy of inception. These properties of weight parameters allow us to pack multiple DNNs into the limited memory by forming weight parameter pages. Weight virtualization takes two steps to enable in-memory multitask learning. The first step is to match DNN weight pages with virtual weight pages in the main memory. The second step is to optimize the virtual weight pages in the main memory in such a way that all the DNN tasks provide the desired level of inference accuracy. Let's take a look at the first step in more detail, which is weight page matching. As the first step, we match weight pages of two DNNs, that is tau p and tau q, in such a way that they minimize the total weight page matching cost C. Here, p and q are the weight page matching sequence of two DNNs we want to find, which minimizes the matching cost on the right-hand side. The matching cost consists of two parts. The first part is the weight value difference between the two DNNs, where the more they are similar, the lower the matching cost we have. The second part of matching cost is the summation of feature information of two weights, which provides their importance. The less they are important, the lower the matching cost we have. This matching cost function primarily encourages virtualization of weights with similar values so that weight pages of similar patterns can be combined together. However, at the same time, the summation of feature information works as a regularizer that discourages too much concentration of highly important weight parameters on a few weight pages in order to ensure the performance of virtualized DNNs by distributing the overall importance of weights over the entire memory. The total weight page matching cost varies depending on the architecture of DNNs and types of tasks. First, when two DNNs of similar architectures performing similar tasks are matched, the total matching cost becomes low. This heat map shows the weight page matching cost between inception and ResNet over all the matching combinations of their weight pages. Here, x-axis and y-axis denote the weight pages of inception and ResNet respectively. The area of paler color in the heat map indicates the smaller matching cost. Next, when two DNNs of similar architectures performing different tasks are matched, here image versus NLP task, the total matching cost becomes higher than the first case due to the difference between the two tasks. Lastly, when two DNNs of different architectures performing different tasks are matched, the total matching cost even becomes higher than the second case. The next step of weight virtualization is to optimize the virtual weight pages matched at the first step in order to provide the desired level of inference accuracy for all tasks. After the first matching step, task tau I is optimized by minimizing the loss function consisting of the original loss of tau I and the matching penalty of its related weight pages. Here, first, LO is the original loss function of task tau I, which is used to train the task tau I without virtualization. Next, the matching penalty is the summation of the matching cost for all virtual weight pages of task tau I shared with other tasks. In more detail, the matching penalty consists of the difference between the current and updated virtual weights and the official information of the current virtual weight. By optimizing DNN tasks in this way, the virtual web pages can be properly updated to work for multiple tasks. In this way, DNN tasks can gain back the possible performance loss caused by virtual web page sharing between them. To evaluate the proposed in-memory multitask learning based on neural web virtualization, we first implemented a multitask mobile robot with an embedded GPU, which performs 6 DNN tasks as shown in the table and photo. As the first evaluation result, the memory usage of 6 DNNs has been improved by 4 times without DNN model compression by packing DNNs whose total memory size is 604 MB into 146 MB of the GPU memory. Next, the virtualized DNNs achieve comparable inference accuracy to the original DNNs that are not virtualized, ranging from a 3% decrease to a 0.7% increase. Also, wave virtualization improves the end-to-end execution time of DNNs up to 36 times when compared to non-virtualization. We also implemented a multitask IoT device based on a microcontroller, which performs 5 scaled-down versions of DNNs. Similar to the multitask mobile robot, it improves memory efficiency, inference accuracy, and end-to-end execution time up to 4 times, 9%, and 176 times, respectively. In conclusion, we introduced a neural virtualization that enables fast and scalable multitask learning of DNNs on resource-constrained systems. We proposed the weight page matching and optimization algorithm, which enables in-memory deep multitask learning. We implemented 2 multitask learning systems, a mobile robot and an IoT device, which demonstrate that memory efficiency, execution time, and energy efficiency increases with weight virtualization. Thank you.